sorry for the delay. There's some technical difficulties. Somebody disconnect the
没有。
cable. So
老师，这个
Is it okay now?
有
Okay. Yeah, so it took us a while to figure it out. Okay, so before we, last time we finished the mcmc chapter, and today we are going to talk about the generalized linear models. Okay, which actually is follow up of the linear regression model. Okay, but before we get started, okay, a few things to announce. Okay, first, I believe the sample final has been posted. Okay, just want you to be aware. Okay, so that's the first thing. Okay, if you want to know, not exactly like the question that will appear in the final, but like the format of the final exam. Okay. The sample final should give you a hint, okay? But don't tell me like, oh, how come the final questions are different? I mean, that's always like that, okay? I mean, I try to make like questions different, okay, every time. So the sample final is the reference, okay, not something you rely on, okay, when you prepare for the final. Okay, you can use it as a practice, for practice purpose, but yeah, don't expect like the sample final questions to appear in the final. Okay, so that's the first thing. The second thing is that the homework 4 has also been posted. If I because I sent it out to the TA. Yesterday, so I believe they already did that. Okay, so the due date is actually let me see, 3 weeks from close to at least more than 2 weeks from now. Okay, so just want you to be aware. Okay, the reason I set it up to be this late is because because of the next reminder, okay, next announcement, which is I will be out of town, okay, for a conference next week, okay. So I will be back, okay, on the 23rd, okay. So we will have lecture on 24th and the 31st, okay. May 31st, May 24th and May 31st, we will have 2 additional lectures, and then we have the final exam, and then the presentation, okay? So this is something I want you to be aware, okay? I'll be out of town next week, so we, excluding today's lecture, we have 2 additional lectures left. Now, after I come back, okay, on the 23rd, okay. So if you include today's lecture, we have 3 lectures, right? So how much am I going to cover for 3 lectures? Okay, my estimate is that, okay, this generalizing linear model, the GLM, is one of the most important topics in Bayesian data analysis, which will be covered in about 1.5 lecture. Okay, and the next chapter I will cover is the model comparison. Okay, which because you can model a question, a problem differently. Okay. So which one is more plausible? Okay, the model comparison will give you some hint, but I suspect we will be able to finish that chapter. So yeah, let's see what I can do, okay, for the model comparison. But and also, okay, I mean, it's if I will only be able to cover a small portion of the model comparison, what I'm going to do for the final exam is that I'm going to exclude that chapter, the model comparison chapter, from the final exam. Okay, in other words, everything that I have covered, from the beginning of the class up to GOM, this chapter will be covered in the final exam, but probably not the model comparison. Let's see how it goes. Okay, if I'm able to finish the model comparison, which is very unlikely, then I'll put it in the final. But if not, yeah, if I'm only going to cover just a little bit, well, let's play by ear. Okay, so back to the generalizing linear model. Okay, from the name, okay, of this chapter, you can immediately get the idea. Okay, this is extension of the linear model. Okay, and we talked about the linear regression. I mean, that was the chapter before the mcmc. Okay, by the way. Okay, so when I say in the last chapter, I'm referring to linear regression, those linear regression model. Okay, we use a linear combination of input variables to predict the mean and output variable. Okay, if you still remember, okay, we do that for quite a few questions. I mean, we cover simple linear regression, we cover multiple linear regression. Okay, so so after we get the combination, linear combination of the input variables, okay, as like a mean, okay, we will assume that's like a Gaussian distribution, the mean of the Gaussian distribution, okay, and we are using Gaussian, okay, for to approximate, like to fit like the data basically, okay, and but this is like the nature of the linear linear regression model. But obviously, okay, you don't have to use Gaussian, right? In different situations, maybe some other type of models, other type of distributions will be more feasible. For example, okay, remember like in the linear regression chapter, instead of using linear regression, okay, we use a student's t-distribution in case if there's some outliers. Remember the S-comp quartet data set. Remember there's like very good like data set, but there's a one point that's like obviously an outlier. If you have that data set and you apply the Gaussian, okay, distribution, it doesn't work very well. But if you replace Gaussian with a student t-distribution, it gives us a very satisfactory result. Okay, so in this chapter we are going to explore that direction. Okay, we'll see more examples where it is wise to use distributions, other than the Gaussian distribution. Okay, actually, okay, if you want, we can consider. We say that's a general motif. Basically, it's a pattern. It's a more general form. Okay, that can summarize a lot of different type of models. Okay, including the models that we covered in the linear regression models, like in the last chapter. Okay, so what is this? Okay, it's something like this. Okay, so the core idea, okay, is basically, okay, we first compute the linear combination of the features, which is alpha plus x beta, right? In here, the x could be a matrix, and the beta obviously could be more than one coefficient, okay? It depends on this is a simple regression or multiple regression, okay? So in the previous chapter, if you remember, okay, we just let this linear combination to be mu, right? And then we assume this mu is a mean of a Gaussian distribution. That's what happens in a linear regression models, right? But now, okay, here, okay, we first assume, okay, alpha plus x beta, this linear combination, okay, we can apply a function f on the result, and then assign that to mu. Okay, this f, okay, in the previous chapter, in the linear regression model, this f is actually an identity function. Okay, you guys know what identity function is, right? I mean, in identity function, if the input is x, the output will be the same thing. Okay, basically, I mean, it doesn't change. Okay, so if it's identity function, obviously alpha plus x beta. Okay, well, the result is alpha plus x beta. Mu just equal to alpha plus x beta, which is exactly what we have in the previous chapter, right? So, but now, okay, because we are considering more general form, so we could apply a function f on this linear combination before we assign it the result to mu. And this f, okay, the technical term of this function f is called inverse link function. Okay, inverse link function. Okay, you may wonder how come it's inverse. I mean, you can probably say, oh, you could call it link function, but why inverse? Okay, we will get to that point later. Okay, so first, for this inverse link function, okay, there are many possible assignment. Okay, as we will see. Okay, depending on our purpose, we can use different functions. But obviously, the identity function was the one that was used in the previous chapter. Okay, so the identity function may not be very useful. Okay, but it allowed us to think of several different models in a more unified way. So once we write this the formula like this, it allowed us to unify not only what we are going to cover, but also the linear regression model. Okay, because function f can be explained as like a identity function. Okay, and then okay, why not just call this f link function? And I mean, to call it inverse link function seems to be a little bit awkward. That's actually because, okay, do we have I'm not sure. Okay, good. That's because mathematically, okay, what usually happens is that we apply a function to mu to obtain the result, that is the linear combination of alpha plus x beta. Okay, and we call this g, we call this function g link function. Okay, this is what we normally do mathematically. Okay, but obviously, okay, once we, now we are writing it in an inverse manner, right? This function f obviously is an inverse function of this g, right? And this g is called link function, so that's why that function f is called inverse link function. Okay? So, just want you to understand where this notation comes from. Okay? So, why we want to generalize that formula? Okay, why do we need to apply a inverse link function? Okay, before we assign the result to mu? That is because sometimes we want to do the some problem, okay, which has a very different nature to the general regression. Okay, for example, okay, if you want to work on a categorical variable, okay, what is categorical variable? Classifications. Okay, classifications. For example, okay, you want to use like certain features to predict, okay, a certain color, such as blue, white, green, okay, or you want to use certain features, for example, the height, the weight, okay, to predict, okay, or to regress, okay, the gender. Okay, gender, it could be male, it could be female, right? So in those cases, the result, okay, will not be a number that is arbitrary, in arbitrary range. So, or there are other examples, biological species, political party affiliations, all these variables, okay, cannot, okay, be modeled by Gaussians because they are categorical variables, right? So, in principle, Gaussian works well for continuous variable, okay, which could have a value on any could have a value. I mean, take a value from like a real line, from the real as long as the result is a real number. So, while the variables mentioned here, okay, are discrete, okay, because they are categorical, they are classifications, right? So, n only take a few values, okay. For example, red, green, blue, okay. Well, I mean, in the categorical variable, I mean, you normally have a limited number of classes, right? Okay. So if we change the distribution we use to model the data, we will in general need to also change how we model the plausible values for the mean of those distributions. So this is like a, something we need to keep in mind. So for example, okay, if you use a binomial distribution, okay, like throwing, like flip coins. We use that, the example we use in the thinking probabilistically and programming probabilistically. I mean, we use the coin flip examples, right? I mean, we use a binomial distribution, okay? So we will need a linear model that returns a mean value in the range of 0 and 1, right? Because the result, okay, of the linear combination of the variables, the input, okay, or features, okay, will be explained, will be considered as like the probability that the coin flip come up head, right? So the probability that coin flip come up head, I mean, that's a probability. So that probability obviously range, is in the range of 0 to 1, right? So, I mean, by the way, for a fair coin, it's more likely that the probability is going to be 0.5, right? We know that, okay? So there are some, limitations. There are some restrictions for this, linear combination of variables. So we need to be able to use, for example, inverse link function to restrict the output to the desired, constraint. Okay, in this case, it's a desired interval, like between 0 and 1. Okay. So the one that we use, okay, to restrict to the range of 0 and 1, okay, is not restricted to discrete variables. Okay, we may want to model data that can only take positive values. Okay, and in that case, okay, you can use like a distribution that will only give you positive values. For example, like gamma or exponential. Okay, this distribution, no matter what value you feed to it, okay, it will always give you a possible value. Okay, so this is like another example that you could have like a different inverse link function. Okay, but okay, and one note that I would like to point out. Remember, we used we just mentioned color as categorical data, right? Yeah, I mean most of the time we consider color as like a discrete result. Okay, it's categorical. Okay, but color can be explained into different wavelength, right? Okay, in physics, okay, for example, okay, if you consider, the wavelength such as 650 nm and 510 nm, okay, each of them represent different color, right? So in other words, okay, a value, okay, even for color, okay, you could explain it as a discrete, as a categorical variable. Or if you try to, model the color by the wavelength, then because wavelength is a continuous, value, obviously, right? So yeah, I mean, you could consider color, okay, the same, variable as a continuous variable. Okay, so which one to use? Okay, it's really up to you. Okay, there's no restriction like you have to use like a variable, okay, as a categorical one or as like a continuous one. Okay, it depends on how you model a problem. Remember, okay, for the same problem, you have different ways to model it. Of course, I mean, these different models may not be, I mean, all good. Okay, some may not be that good. Okay, some may be better. Okay, I mean, when we talk about the model comparisons, I mean, we will, you will find like how we can compare, I mean, different models. But for now, okay, I just want to point out, okay, for a variable, okay, whether or not it's a categorical or continuous, it really depends on how you model it. Okay. And if you want to model, or if you want to, convert a value, okay, to a range between 0 and 1, okay, into 0, the range of 0 and 1, okay, then the inverse link function that you would like to use, okay, in general is logistic function, okay, and such regression is called logistic regression. And the situation where you want to convert the linear combination of variables into the range of 0 and 1, most likely it's because just like the coin flip, right? I mean, we want to convert the result into 0 and 1. And the theta, what does the theta? What is the nature of the theta? It's a probability, right? It's a probability. I mean, so the same thing applies here, okay? You basically want to, how should I say, like, want to deal with a problem that's like, yeah, we are dealing with a categorical problem, but this is a binary classification. Binary classification, okay, because as I said, it will output probability, right? Okay, once you apply the logistic, okay, function to your linear combination of the variables, the result will be in the range of 0 and 1, right? So it is a probability. So if it's a probability, you can explain that probability as if you have two classes, and assuming these two classes are exclusive, meaning, okay, if the result is A, it wouldn't be B. Okay, if it's a B, it wouldn't be A. Okay, if the result is like exclusive, then okay, you can say that the probability, okay, that come out of this logistic inverse link function is the probability that the result is the positive class. Okay, so this is like how we consider this. Okay, you know, and first, like, no matter what you are talking about, like you are talking about linear regression models that we cover in the last chapter, or the logistic regression that we are going to, the example that we are going to talk about, they all belongs to the supervised learning in machine learning field, okay? Because like in some sense, we are trying to use the known result, okay? We know the training, the result of the training set, okay? And we use that the training set to train a model, and we use that model for prediction, okay? So because the training set, okay, the instances in the training set has like we know the answer to each of them. So this is considered as a supervised learning. Okay, in supervised learning, basically we find a mapping between the output and the input variables. Okay, that's the concept of like supervised learning.